Hello and welcome. Thank you for joining me. My name is Alon Sela, and today we're going to continue talking about the Langevin stochastic differential equation, and we're going to continue where we've stopped. Let's do a small recap. We said that this is the Langevin equation. We said that eta at time t is a Gaussian white noise. It has these properties. The expectation of the process at any given time t is equal to 0, and this quantity here, which is called the autocorrelation function, is equal to some constant gamma times the Dirac delta function. We saw that the solution to the Langevin equation, and by solution we mean finding expression for the velocity at time t. The solution is given by this expression. We saw that the expectation of the velocity at time t is equal to v naught some initial condition, some initial velocity times e to the minus gamma t, and we found the second moment, the expectation of the velocity squared. We saw that we can write it in two different ways. Basically, this is the first way, this is the second way. They are equivalent. And today we're going to finish this analysis by calculating the variance. So let's start by finding the variance for the process. So the variance for the process, the variance is the second moment, which is the expectation of the squared of the velocity minus the squared of the mean, and the mean is this. So this is the variance, the expectation of the squared velocity minus the squared of the mean of the velocity. We found this both of these quantities, so let's write them, let's plug them in. Let's see. This expression right here we found out in the last video, so let's use this first one. It's okay to use this one also. I'll use this one. So let's see, we have, let's change color. We have v naught squared e to the minus 2 gamma t plus gamma over 2m squared gamma times 1 minus e to the minus 2 gamma t. This is for the expectation of the squared velocity minus the squared of the mean of the velocity. The mean of the velocity is this, so we need to square it. So we need to square this quantity, but squaring it is basically putting 2 here. So we have minus v naught e to the minus 2 gamma t. So now let's see what we can do. Of course I missed here the squared also. The square is going for this also. Let's do it again without making any mistakes. Let's see. So this is what I'm looking for. So we have v naught squared and we have e to the minus 2 gamma t. So now we can see that this term will cancel with this term, and we are left with this. So the variance for the velocity at time t is equal to gamma over 2m squared gamma times 1 over 1 minus e to the minus 2 gamma t. So basically we have both of the mean, we have the variance, and one quick important note. Look at this right here. This thing is constant, and this thing right here is integral for Gaussian white noise. And because this is an integral Gaussian, because this is Gaussian white noise, the integral of Gaussian white noise is also Gaussian, meaning that this process is Gaussian, and therefore we can write that the velocity at time t, the distribution, is a normal distribution with the expectation v naught e to the minus gamma t, and variance of gamma over 2m squared gamma times 1 minus e to the minus 2 gamma t. So these are the important statistics for the velocity, which are derived from the Langevin stochastic differential equation. Now, an important step or let's say it the other way around. If we want to continue this process by calculating this constant gamma, we need to do the following thing. So we need to make a connection between this Langevin stochastic differential equation and the Maxwell distribution for a particle's velocity. So even though if you might not know and understand what the Maxwell distribution is, let's try to write it in its simplest form, without making any without elaborate about this distribution. Let's just write it. So according to Maxwell distribution, we get that velocity of a particle, I'm writing here small m for the distinguish between this this velocity which we found and the Maxwell distribution velocity. So this is the velocity for the Maxwell distribution, and it is normal with expectation of 0 and k Boltzmann t over m for the variance. Now k Boltzmann stands for the Boltzmann constant, t is the temperature, and m is the mass. But basically I don't care about if you understand this quantity or not. This is some constant, this is another constant, and this is another constant. So basically this whole quantity is some constant that represent the the variance for this process. So now I want to make the connection between the Maxwell distribution and the Langevin stochastic differential equation for the velocity. So we are saying this next statement. We are saying that the particle starts at some velocity, and as time goes by, meaning as t is becoming larger and larger, we want the distribution for the particle to we want it to converge. We want it after a while, after enough time have passed, we want the distribution for the velocity given by the Langevin stochastic differential equation, we want it to converge to the Maxwell distribution. Meaning we want that as t become very large, we want to get the statistical properties of the Maxwell distribution. So we are going to do the next thing. Note that because the expectation for the Maxwell distribution is 0, the variance for the Maxwell distribution, the variance var of Vt m for the Maxwell distribution it's equal to the second moment v squared t of Maxwell minus the squared of the expectation, but the expectation is 0, so this is 0, and we are left with the fact that for the Maxwell distribution, the second moment is the variance. So and the variance we saw, this is the variance. So we are saying that the second moment for the Maxwell distribution is k b t over m. So this is what we want also for the second moment for the velocity from the Langevin stochastic differential equation. So let's see, the second moment for the Langevin from the Langevin equation is this. So we are saying that we want for the limit as t goes to infinity of the second moment of the velocity from the Langevin equation, we want it to be equal to the second moment for the second moment from the Maxwell distribution, which is k Boltzmann t over m. Okay, let's make some room. Let's take another color, and basically what we've said right now implies that we want the limit as t goes to infinity of the second moment, which we saw the second moment is v naught squared e to the minus 2 gamma t plus gamma over 2 m squared gamma times 1 minus e to the minus 2 gamma t. We want the limit of this expression to be equal to k Boltzmann t over m. This is what we want if we want the velocity statistics be consistent with the Maxwell distribution. So let's see. As t goes to infinity, this thing right here will go to 0. T will go to infinity, meaning this entire thing will go to infinity. E to the minus infinity goes to 0. So this will go to 0, which means this entire thing will go to 0 in the limit. Also this thing right here will be infinity. E to the minus infinity is 0. It will go to 0. And we will be left with gamma over 2m squared gamma equal to k Boltzmann t over m. Now let's simple multiplication times let's do 2 times m squared gamma. So this will go, we will be left with gamma equal to k Boltzmann t over m times 2m squared gamma, and this will go with one of these, so we are left with gamma equal to 2m, we have 2, we have 1m gamma k Boltzmann t. So this is the expression for gamma. It's a constant. We have 2, we have the mass, we have the coefficient friction, we have Boltzmann coefficient, I'm sorry, Boltzmann constant, and we have the temperature. I don't really care about this, or I don't care about what, if you know about what is the coefficient friction, what is Boltzmann constant, and the temperature. What I want you to take from here is that this gamma is some constant, and if we want, let's take another color. If we want that this process m v dot is equal to minus m gamma v plus eta, which is the Langevin equation, if we want that the Langevin equation for a particle's velocity, if we want it to be consistent with the Maxwell distribution, we must demand that, as we saw, let's write just one more thing. We saw that eta at time t, the expectation, is equal to 0, and we saw that this quantity, which is the autocorrelation function, is equal to gamma times the Dirac delta function. And now we found an expression for this gamma, so basically we are saying that if we want that the Langevin stochastic differential equation for particle's velocity if we want the velocity, the statistical properties of this process to be equivalent in the long run to the Maxwell distribution, we must demand that the autocorrelation function will be of this form. We want 2m gamma k Boltzmann t times the Dirac delta function t minus t prime. So this is the key point for the connection between the Maxwell distribution, which is we saw it's with the expectation in 0, and the variance is k Boltzmann over m. So if we want our particle, which is given, which is its velocity is driven by the Langevin stochastic differential equation, if we want it to be equivalent, we must demand that gamma, a large gamma, will be equal to 2m gamma k Boltzmann t, and this will bring us to the fact that the autocorrelation function for this which represent the Gaussian white noise, its autocorrelation function must be of this form. And let's see. So let's summarize what we've done and said. We talked about the Langevin stochastic differential equation, which is given by this process, this entire process. We said that eta at time t is a Gaussian white noise with an expectation of 0 and autocorrelation, which is given by some constant times the Dirac delta function. We saw the solution for the stochastic differential equation, which is v at time t is equal to this expression. We saw the expectation for the velocity and the variance for the velocity, even though we didn't write it specifically. Actually, now will be a good time to write it. So we said that for the Langevin stochastic differential equation, the velocity at time t is a Gaussian process with expectation v0 e to the minus gamma t and gamma over 2m gamma 2m squared gamma times 1 minus e to the minus 2 gamma t. And we've just found gamma. We found gamma using the fact that if we want this process for the velocity to be consistent with the Maxwell distribution, with these properties for the Maxwell distribution, at the long run, we want the second moment to be as the second moment for the Maxwell distribution. And this fact led us to find this gamma, which we saw is 2m gamma k Boltzmann t, and now let's replace it here. So finally, if we want to be consistent with the Maxwell distribution, we got this thing right here. Let's see, instead of gamma, we said that gamma is equal to 2m gamma k Boltzmann t, and this is over 2m squared gamma times 1 minus e to the minus 2 gamma t, and now this cancel with this, the gamma cancel with the gamma, the m here is cancelled with one of these, and we are left with k Boltzmann t over m times 1 minus e to the minus 2 gamma t for this is the variance. And note that when t goes to 0, this expression will be 0, this will go to 0, this expression will go to 0, which means that this expression will go to k Boltzmann t over m. So this concludes our analysis for the velocity given by the Langevin stochastic differential equation. I hope you enjoy this video, and I invite you to join me to the next videos as well. Until then, I'm Alon Sela, and I wish you to continue enjoying the world of mathematics and probability. Bye bye.